Hello and welcome. I'm Barton Poulson, and this is the datalab.dc live office hours. And tonight, we're going to talk about keeping things simple in your data work, keeping data analyses, data processes, models, and interpretations simple and workable. And before we get started in our little half-hour session, I would like to invite you to say hello and tell us where you are. Put a comment in and tell us where you are. I am in Salt Lake City, Utah, and it is 8 o'clock at night and it is dark. So I cannot go out and ride my bicycle after this event. But I would love to know where you are. Santiago, thank you for saying hi. Tell me where you are. That would be great. And is there anybody else out there? Or is this going to be a private little chat between me and Santiago and the people who get to watch us later when we're have the recordings available? Santiago's in Mexico City. It's 8 o'clock. We have a user in South Dakota where it's going to be colder than it is here, and Corpus Christi, Texas, and Toronto. Where else are you all? Columbia and Dallas. Oh, this is wonderful. And then College Station, Texas, and British Columbia. You know, what's funny is I chose this time because I thought it would work better for people in the Eastern Hemisphere, uh, Eastern Europe and India and Africa. And as far as I can tell, it seems to be working better for people who are right here in my same area. I have Indianapolis and Chicago. Thank you so much for joining me. And I realize for some of you, it's probably pretty late where you are. And it makes me wonder if maybe in the future I should do these just like an hour or so earlier. Oh, well, okay. Here we have our one person from India and, well, from Jakarta also so far. Folks, thank you for coming. This is a really nice thing for me because, you know, I'm a university professor and I teach my classes. I've got several hundred students, but it's I don't have interaction the way that I am used to because it's online. And well, that works very well for my students, and they're all watching at different times. But it's nice to have this live session with one another. Oh my goodness, Irene in Japan. Thank you so much for connecting. Well, let me tell you a little bit about what I want to talk about tonight. And that is about keeping your work simple when you're doing things. Now, there's a saying you've probably, it actually comes from the architect Ludwig Mies van der Rohe, less is more. About now, he's talking about a kind of design aesthetic and architecture having simple shapes and as opposed to the very elaborate old world Rococo kind of designs. He made very blunt stuff. And truthfully, since here in the Western United States, everything is new anyhow, it's a style that I'm comfortable with. Um, but when it comes to your data work, the idea is to make things as simple as possible, but no simpler, meaning you have a responsibility to address the data sufficiently. I mean, the trick is data analysis is a simplification. That's if you weren't simplifying it, you wouldn't analyze it. You would just tell people go out there and see it on your own. But your responsibility is to take this massive data, this huge, giant, confusing thing, and get it down to its essence so you can get probably one or two or three actionable insights for the people who requested the analysis in the first place. So their goals are pretty simple. They want to say, how much should we charge for this? When should we be open? What items should we recommend to people? What are the best ways to reach donors? Those are basically pretty simple questions. And I realize that in some situations, the methods are inherently going to be very, very complex. If you were doing a data science product and you're using complicated machine learning methods, well, it's going to be big and it's going to be complicated. And there may be situations in which that is appropriate because that matches the precision that you need. On the other hand, I mean, that's a situation where the machine is usually what is implementing the decision. It's processing the data. It is coming around and it is recommending this item. It is suggesting this price. It is scoring this applicant in this way. Fine, it'll do that on its own. But there's a whole other world, and that is where you are doing analysis for human makers. And that's where I work. I don't do data products. I work with people who run large corporations, who work in governmental organizations, who have small nonprofits, and they're trying to make decisions how best to work on a global uh, campaign to build confidence, or how to, again, how to reach out to donors, or simply know what days they should be functioning. And in those situations, my job is to take the data and it's to give these people an answer. Now, in this process, anytime you're working with your data, you have to make a huge number of decisions. You have to decide whether your model is going to fit the data correctly, or correctly is not the right word, appropriately. Because one of the funny things about data is there really is no correct. Everything is, because it's a simplification, because you are changing the way you deal with things, it's a matter of, is this simplification, is this approach useful? Is it insightful? And is it true to the data? I mean, everything's going to, like I said, everything's going to simplify it. When I talk about keeping your data work simple, what I am mostly talking about is using simple methods like linear regression, which everybody's had experience with. Linear regression, you're trying to predict a quantitative outcome, say, for instance, trying to calculate a score for somebody, and you've got a collection of variables, and you can build a simple linear model that says, take this variable, multiply it by this, take this variable, multiply it by this, add those all up, and you get your score. Linear regression, basic linear regression, which means you're taking one variable and a coefficient at a time, adding it together, maybe no interactions, maybe no transformations, maybe all the variables are at one level. A basic linear regression is a wonderful method. It's very simple and it's very robust. One of the things that works so well with linear regression is that it is less sensitive to some of the variations that other methods do. You may know, for instance, about spoofing the machine learning algorithms that categorize text or sound or images, that it is possible to create methods where you change just a few pixels in a photo, or you add a sound and audio track that's imperceptible to humans, but the machine learning algorithm picks up on it, and you can get crazy results. You can wear eyeglass frames that convince the algorithm, the computer, that you're not a person, or that more I don't know if that's worse, the one that tells it you are a specific other person who's different from you. Those systems are very sensitive. People who have worked with neural networks know about how important it is to choose the parameters and the hyperparameters that govern the system, and that it can be very sensitive. Linear regression is not so sensitive. It is a more robust, more stable method. And so when you're doing an analysis, if you're trying to predict a quantitative outcome, I would say always, always run a straight ahead, you know, you have skewed variables. It may be that you have dependencies between variables. It may be that you have data at multiple levels, and that you also have data of different types. So for instance, maybe you've got quantitative predictors, and maybe you've got ordinal or even categorical nominal predictors. linear regression is able to handle all of those, but you can adjust it for those, and sometimes you don't even need to adjust it. You know, um, another one is if you're calculating descriptive statistics, always do the mean. Now, there will be times if the data is skewed or if the data has strong bimodal shapes, the mean is not going to be very helpful, but you should always calculate it so you have it as a reference point, especially because so many other procedures that we use, like standard deviation and variance, like correlations, like regression coefficients, all involve the mean. You want to know what you're dealing with there. Um, Other things like bar charts and line charts are very simple, and you would want to use those as well. And so let me ask you guys a question. When have you had to choose between methods to work with data that were simpler, more basic, or methods that were more complex? So, for instance, if you were working on a master's thesis, or if you were working on a very large scale project for your organization, when did you actually have to sit down and think deliberately about some of the methods for preparing the data, for getting basic descriptives, for visualizing the data, or for building models? I would love to know what some of your experiences on that are. And I'm not expecting anything massive here, but if you're able to give an example from your own work where you have had to make those decisions, that would be great. While you're working on that, I can tell you two places that this showed up all the time in my work when I was in graduate school and when I'm doing basic academic research. Because I am an experimental psychologist by my background, um, we use a lot of surveys. And when you give people your surveys and you are trying to combine the data, um, there's a question about what method you use to group the variables. And the most common choices are factor analysis and principal components analysis. They're very, very closely related, even though they have different theories about the relationships between the observed variables and the underlying things that you're talking about. But then there's a million other decisions you have to make about rotations and about whether you're going to weight your data according to the eigenvalues, against the coefficients that you get. Um, and that is one decision that we have to work with all the time. How are we going to combine the variables? And I'll talk about that in a minute, but if you have an example of your own data, again, could be a project from school, could be a project that you did at work some time ago. But if you have a situation where you have had to choose between different methods, it would be wonderful if you could share that with us. So if you can put a comment, that would be great. In the meantime, welcome to Fabio, checking in from Brazil, and to Supan Nguyen from Myanmar, and to Bosun Park from Korea. Again, I'm amazed at how people connect from all over the place. Thank you for joining me. But if you're there, tell me some of the times you've had to make choices, or sometimes you weren't sure what was going to be the best way to go about something. I'll give you a minute to think about that while I have a drink of my water. Okay, Santiago says this. Mixed marketing modeling had to measure the effect of each media strategy and had to decide whether to apply linear regression, time series, XREG SARIMA, that's the seasonal adjusted regression integrated moving average model, and using deflation factors to take into account the duration of a media effect. Okay, do you know what? Time series modeling is a really big thing. The variations on the ARIMA models will show up in there. And whether to apply a straight ahead linear regression, which depending on whether that's part of your time series or something else, it can be, you know, when I'm working with time series, so you've got a scatter plot, and you've got, this is the value at this time, at this time, at this time. So for instance, I get I get royalties, and I get them. I get a royalty report every month, and I'm able to chart that. One of the things I found is that sometimes you can run an absolutely straight linear regression line through it. It feels like you're hitting it with a 2x4. It feels like the most boneheaded way. But there are times that a straight line is, in fact, a reasonable approximation of the trend. Other times you have to go with something that's more complicated, like you have a growth curve, or you'll have seasonal adjustments, which you'll have in an ARIMA model. Um, and there are times that you will need to make those. But seeing if just a totally straight regression line works is going to be your best first bet. Um, and then, by the way, Santiago, since you mentioned this, what decisions did you make? And really, did you notice a difference? Did you try more than one approach, and did you get different results? Did you get different insights? Was one of them obviously a poor fit, and was another one obviously a better fit? That's a question, because when if the models aren't dramatically different, go with the easier one, go with the simpler one. And the reason for that, I'll say that, is simpler models, again, a straight ahead linear regression model. Simpler models have a couple of things going for them. One is they're easier to calculate. Um, a straight ahead linear regression is very easy to do. I like it when I'm in R, if I set up the data so that my outcome variable, I just call it Y, is at the very beginning of the data frame, and everything after it is a part of the X matrix, the predictors. I have like 4 letters I have to type um, in order to get a basic regression model. It's beautiful. But linear regression, the simpler the model is, the more stable it is. That is, the less susceptible just to get thrown off by some of the small quirks in the data. And also, the more generalizable it is. And that's a tricky one, because if you've worked in machine learning, you know about the risk of overfitting. But let me come back to that in just a second. Santiago followed up and said, linear regression clearly underperformed since seasonality was very strong. That makes sense. I see that in my royalties data, because a lot of the people who watch my stuff are students. We have the stuff going up and down about whether school's in session and what time it is. So when you have strong seasonality, it's going to make a big difference to be able to have a model that can put that in. So a SARIMA model is going to be a great one. Preferred media strategies that were used more often in high sales times of years. That makes a lot of sense. And so that's a nice one too. But the other thing also is, um, you have many different ways of doing ARIMA models. You can do neural networks on these, and they can be um, amazingly perform amazingly well in certain circumstances. But I found, in my own experience, the basic ARIMA model, or SARIMA model with the seasonal adjusted, um, it was really nice because you could actually see what the coefficients were and see what went into them. Um, Anybody else have experience with this? If you had to choose between methods that were simpler and methods that were more complex, I mean, even seriously, a bar chart versus um, a grouped bar chart could be an example. But what you find, so if you can respond to that, that would be great. But what you find is that the simpler the method is, usually the more generalizable it is. And I gave the example in my own work about how when you have survey data, when you have many different variables that you're trying to combine, usually with a principal component analysis, one of the funny things that comes up in that is you get these big tables of coefficients. Say, for instance, you've got 30 variables, and you might get 5 components out of it. And what the table will have, it'll have the 5 components. That is the ways that you can group the variables. And you'll have those 5 components in columns, and then you'll have 30 rows, one for each of the variables, and will give you a coefficient. It says multiply this variable times this number and multiply this number times this variable, and then you add those all up to get the component scores. I've never met anybody who's actually done that in real life. Nobody has used, I've never seen an application. I'm sure it happens, but I have never been part of a situation where people actually used the coefficients in the table as anything other than, is it big, or is it functionally zero? We use a cutoff of zero point 0.7 usually. And what you would do from there is you would then convert it to what are called unit weights. If the absolute value of the principal component coefficient is greater than zero point 0.7, so positive zero point 0.7 or higher, or negative zero point 0.7 or lower, then you simply convert that to a positive one or a negative one. And if the absolute value is less than that, you just treat it as zero. And so you're taking something that is measured on a continuous scale and you're chopping it off and turning it as unit weights. One of my favorite statistical articles that I read in graduate school, unfortunately, I've found it before, but off the top of my head, I believe the title of the article was Unit Weights, It Don't Make No Never Mind. What they're saying is it doesn't matter. And the risk with that is you get, when you tailor your analysis to 2 or 3 or 17 decimal places of your data, you are at a great risk of, again, what's called overfitting. That's something I mentioned earlier. Overfitting, which is a very big concern in the machine learning world, is when you develop a model. It could be a regression model, it could be a decision tree or random forest, it could be any of a number of things. But you develop a model that is so specific to the one data set that you trained it on that it can't go anywhere else. Think of it, it's like wearing somebody else's shoes. If they've broken them in, maybe you would have bought the same shoes before, but if they've broken in them in, you don't want to wear somebody else's shoes that are adapted to their feet. My feet are weird. That would be really uncomfortable. And then overfitting is like it's worn into that exact data set and it doesn't generalize well. And so what you find is, by backing out a little bit, by not using so many decimal places, by reducing the number of coefficients, the number of factors, the number of interactions that you have, by getting a simpler model, you can get one that generalizes better to new data sets. Now, in the machine learning world, the way you deal with that is pretty simple. Um, when you get a data set, you split it into 2 or 3 parts. You split it into usually the testing data set and a training data set. You can also have a validation data set, but the test and train is the most common. And the idea is you take a large chunk of the data, maybe 70%, and you put that in the training data set. And that is the data that you develop your model on. And it's also very common in that training data set to do cross validation, where you split that data set into several pieces, maybe 7, maybe 10, maybe 12, and you rotate through it and you take each piece and use that as the outcome while you build a model based on the others, and you cycle through. And so you do many, many sets of models. And what that does is it helps reduce some of the overfitting that can happen in the training situation where you're developing a model to fit the data. And then that gets it back. Again, it's like, instead of fitting the shoe, breaking it into just one person, it's making it so it works for many people. And then it adapts it, excuse me, and then you can take that model and it will usually perform better against the new test data set than any one of the individual models. So by going through this iterative process and then combining your results, you're going to get something that is actually a little simpler. It's going to, again, it's like going to fewer decimal places. It's making something that doesn't have as many curves, doesn't fit a specific, that one shape. Um, Similarly, I am a huge advocate of, when you are presenting your results, I am a huge advocate of making very basic presentations. I use bar charts and line charts all the time. I mean, all the time. As far as I'm concerned, um, you have to have an excuse that you can write down, that you can like submit a request if you want to do something other than a bar chart or a line chart. And part of that is because when you use those methods, bar charts and line charts and a basic regression model and basic unit weighting in a principal component analysis, those things are very easy to explain. They're very easy to troubleshoot. They're very easy to modify, and they're very easy to replicate. And all of those things are going to be important in terms of getting a data analysis that is generalizable and is explainable and then is actionable by your clients. That's the goal. So I use them because I have the most confidence in them. That also means that I'm able to explain them. I understand very well what's happening in them. I am able to calculate an ARIMA model for time series. I cannot explain it as well as I can explain linear regression or the analysis of variance. Those ones I can do in my sleep. Um, and so I, in part, rely on the methods that I am most comfortable with, that I have the greatest confidence in, and that I'm able to explain. I find that makes the work a little simpler and a little more effective. We only have 2 more minutes. And so I just want to mention one other thing. I am aware that the choices that you have are often affected by your organizational policies. They can be affected by software restrictions or by common professional practices. So, for instance, organizational policies, they may simply say, we use Minitab and we use this analysis because it's what we've done for the last 8 years, and we're going to keep doing the same thing. Okay, fine. That's what they're going to do. Software restrictions. The funny thing is, I use Macintosh computers. I have a license for SPSS, and so I also have a license for Amos, which does structural equation modeling. But I've never had a Windows computer, and Amos is a Windows only program. And while I know there's ways to get around it, it just means I've never done SEM. Not in Amos. I have done SEM in R. Um, and so it affects the way that I do things, but I've often felt that multi-level models were not necessary for what I was doing. And then common professional practices, when it comes down to doing the analysis of scales and doing principal component analysis or factor analysis, there are practices that are very common in my field in research psychology, and they're going to be different if you're doing econometrics or if you're doing medical research. You're going to have standard practices within your field that are going to answer some of the questions for you. So our time is nearly up, but I just want to repeat this one thing. A simpler model, you're going to be able to explain it better, you're going to be able to troubleshoot it better, and it's going to usually generalize better. It needs to fit the data. Like the example we had, if you have a strong seasonality over time, a straight line is not going to be appropriate. But a seasonal model can capture that variation, and that is still considered the simplest adequate model to match your data. So you want to try to keep it simple, and that's going to give your work the biggest impact with your stakeholders. And with that, folks, I want to say thank you so much for joining me in this very brief session, and I look forward to seeing you again in a few weeks. Thanks so much. Bye-bye.